Okay, well, the way I've got this drawn, the signs are a little bit confusing, okay? Pluses and the minuses. Of course, in statics, you're used to confusing things. Because you deal with right triangles instead of circular model. But we'll reconcile it all, but let's go to this picture here, okay? Now, here theta is less than 45, or less than whatever the arctangent of dy over dx is, right? So that for this triangle, we've got dx here, and we've got theta here, and we've got a right angle. Okay? So what's this side?
dy sine of theta.
dy tangent of theta.
Or yeah.
We don't have the hypotenuse. The dx tangent of theta. Okay? So the hypotenuse is dx times the square root of 1 plus tangent squared theta, which is secant squared theta, which is dx over cosine theta. Okay? And you can check that out. Okay? It's going to be the arc sine of this over this, right? Or sorry, this over this. Well, this over this is just sine theta. So this angle should be the arc sine of sine theta, which it is. Okay? Or if you prefer, this over this should be the cosine of theta, which it certainly is. Okay? Okay, so we have this. Now, the change here delta F due to dx is fx dx, right? It's Fy times dx tangent theta, right? Okay? So delta F is Fx plus Fy tangent theta multiplied by dx, right? I mean, you add the change in F due to this plus the change in F due to this, right? Okay? So delta F over delta X is what? Or over delta, not delta X, over delta S, where delta S is your displacement along this line. Okay? So we're going to call this delta S here. The length of the hypotenuse of this triangle. Delta F over delta S is what? Delta S is dx over cosine theta. Okay? I mean, obviously, if you divide by cosine of theta, and that looks kind of like a 0, doesn't it? You're going to get a cosine theta here. You're going to get tangent over cosine times cosine, which is sine, right? So that's trivial, but you might have to write it out to convince yourself. Okay? So this is rate of change of x with respect to displacement in direction theta. And all it is, there are more intuitive ways to think of this. If you got any displacement here, okay, well, that displacement has an x component that's delta s times the cosine of theta, and a y that's delta x times the sine of theta, right? Well, if you multiply fx by this and fy by this, you get the total change. I could have done it that way. But I'm going to kind of leave it to you to do it that way. This is a little more complicated, that one's a little more obvious, but it works out either way. Okay? You believe me?
Yeah.
Yeah, you got to work it out. Okay, 'cause it's central. Okay, this differential and this thing are central, because this thing now tells you the rate at which the function changes in any direction. You know, it's whatever theta is, whatever the angle of that direction is with respect to the x-axis, there it is. Okay? Well, we call this the directional derivative, which ought to make a lot of sense. Okay? Directional derivative in the direction theta. Okay? Now there are other more elegant ways in terms of like dot products, and I'm going to do that too. I want you to understand this in a variety of ways.